Okay, everyone. Today we will have a look at the modes of failure, different types of mechanical failures. When we talk about the modes of the failure, there are multiple modes of the failure. Fracture, it can be fatigue, it can be creep. So these are the different failure modes. Sometimes we classify the modes of the failure based on it's a ductile failure or it's a brittle failure. So we can also have a look at if it's an intergranular failure or transgranular failure. Now, last time we did have a look at the grain structures. Now, there's only one grain structure that is visible to naked eye. I'll just put something here that disappear now. Sorry. Again. Yes. No. That was grain structures on it. Okay. So fracture toughness. We also have a look at the fracture toughness. We also have a look at stress concentration. Like what's the stress concentration? The more the stress concentration at any point is, that can result in failure. Now we will also look at how the crack actually develops and how the crack actually propagates. Now when we have a look at the fracture modes, how do we define the fracture? A fracture is when a body is split into two pieces. Yeah, if they're not split into pieces, like it's still half, that's not classified as fracture. Fracture, they have to split into two pieces. And the reason it's split into two pieces is because you have applied a static force, you have applied a stress on it. We can do that one as at high temperature, or we can actually do that one as low temperature. Now, TM states the melting point of a material. Okay. Now, fracture modes depends on the material ability to deform under force. Now, there are two types of deformation. One is called the plastic deformation, and the other is known as elastic deformation. Plastic deformation is a type of deformation where where when the material is deformed, when you apply the force, the material is deformed, it no longer comes back to its original position, even if you remove the force. Elastic deformation is like as an elastic band. You apply the force, you stretch it, you release the force, it will come back to its original length. Now, then we got two main classification of fracture modes. The main one is the ductile failure and the brittle failure. Ductile failure, when if a material is ductile, when you apply the force, the material will stretch. When the material will stretch, it will deform and it will stretch further. You increase the force, then you will reach a point where the material will no longer come back to its original shape. And you keep stretching, it will create a necking region, and then the material will deform. Now, it will have a massive, after failure, if you have a look, the material will have a change in length, change in cross-sectional area. Brittle failure, like glass, if you apply the force on the glass, they will break. If you have 1 meter glass and you break it, you put it together, it's still going to be 1 meter with the pieces put together. The thing is, because there is no plastic deformation, it's a sudden catastrophic failure. In engineering application, we prefer ductile failure because it gives us some warning before it actually fails. What actually happened to the fracture mechanism? Now, the way the fracture propagates, initially we apply a force. The force converts into stress depending on the cross-section area. It forms a crack, and then the cracks propagates. When the crack propagates, then that can cause a failure. Ductile failure will have extensive plastic deformation closer to the advancing crack, in the vicinity of the advancing crack. The process in a ductile failure propagates very slowly. Now, as you increase the stress, the crack will propagate. As you increase the force, it will propagate. But in brittle failure, the crack spread very rapidly. Initially, there will be a crack, and then when you apply a force, the crack will spread massively rapidly. The crack will start to finish in less than 1 microsecond, in less than a second, which means it is not going to give you any warning. So there will not be any warning, and the material will be catastrophic failure. The crack propagations. In brittle, the way the crack propagate, the tip is always going to be sharp one. The crack always propagate. In plastic deformation, as you can see in the picture on your right side, the plastic, we always have a deformed region where it's going to deform the region, and then it will crack will propagate. Okay, now we call it energy balance on the crack. What does it mean by energy balance on the crack? Every crack will balance some kind of energy before it actually propagates. It will either transfer the energy to cause the elastic deformation, or it will transfer the energy to cause a plastic deformation. In ductile, energy is transformed to create a plastic deformation. There's a thing called elastic strain energy. Elastic strain energy is energy stored in the material when it is elastically deformed. This is released when the crack propagates. Every time you create a new surface, you need to spend some energy. For example, if that is some material, I break it down, now it has created another surface. So this another surface creation requires energy, which I have actually used. Hence, there was a failure. Now, how does it look like, ductile versus brittle failure? This is first one, yellow one, it says very ductile failure. This is a very super ductile failure. The second one is a moderate ductile failure. The third one is a brittle failure. Yeah. This percentage AR mean area reduction, percentage area reduction. And this percentage EL mean percentage elongation. So we got percentage area and we got percentage elongation. In a very ductile material, you have a massive high percentage area reduction. Look at the percentage area, it's reduced. It was normal and it reduced to that shape. This is very ductile. And percentage elongation, the material will elongate massively. Now we look at the moderate ductile. It's like a typical cup and cone failure with a fibrous, if you look here, that's a fibrous kind of failure. In brittle failure, there is no change in the percentage area reduction because you can see the cross-section area is same and the length does not change as well. Ductile will give you a warning before it fails. Brittle is not going to give you any warning and it will fail. Now, what actually happened? Different steps, different what goes on into the material or ductile material. First thing what you do is when we apply a force on any material, you stretch it. When you stretch the material, what actually happened? You apply a force. When you apply a force and you keep increasing the force, the first thing that happens is the necking will appear. Necking is reduction in cross-sectional area. You still keep applying the force, it will create the void, which are tiny gaps in the material that will appear. Yeah, void nucleation will take place. Then the void nucleation will combine together and they will actually create a cavity. And if you actually, the material is still strong, it's still going to hold. And then you still apply the force. Now what will actually happen is the crack will propagate. That when the crack propagate, it will propagate in 45 degrees. So this angle is around 45 degrees for a relative ductile material, and the material will fracture. In a typical material, you will see a cup and cone failure. So this is a cup on the top, that the bottom one, this one, it's a cone. Yeah. So this is 100 millimeter. It's just a magnified version of that one. If you have a look at this bit, these are the voids. These are the micro voids that have been created. Depends. We are applying a normal stress. Normal stress is a stress that's been applying 90 degree to the material where it actually fails. Sometimes there's a stress known as hoop stress, H-O-O-P, the hoop stress. And that stress does apply, then it can cause a different types of failure. We talk about that one later. Now, if there is a pipe ductile failure looks like that, it's a one large, single large deformation. But if we have a look at the brittle failure, in the brittle failure, you can actually see it actually break down into multiple failures, many pieces, but very small deformation. Okay, here you go. This is an example for cup and cone failure. In cup and cone, this thing is called the cone, and this part is called the cup. When we look at the brittle failure, there you can see there is no reduction in cross-section area, and you can also see the ductile brittle surface looks very shiny. When we do a scanning electron microscopy, the way it look is like this. Now, this is scanning electron microscopy. On this one, you can actually see the fibers being pulled out. You can see the fibers being pulled out. Yeah. This is the uniaxial, which means one axis, tensile loading. Okay. Now, the next bit. When we do failure analysis, we can actually pinpoint the area where the failure actually occurs. We can have a look at from where the failure starts. So if you have a look at this point, you can actually see the V shapes. You can actually see the V shapes. It's quite difficult to see, but yeah, you can see the V shapes. It's pointing towards here. This is where the cracks start to originate. So when you do aircraft failure investigation, they can pinpoint where the failure actually starts. And on here, you can see that that's where the failure actually starts. We call that one chevron marking. It's exactly the same marking that or beach mark, the one that appears on beach when the water comes and goes down. So this is called the beach marks or chevron marks. Now we talk about the intergranular and transgranular. We talk about the grain boundaries. Let's have a look. Let's stick it to the page. Now this is the only grains that you can actually see from your with your naked eye. These are the grains of zinc. So if I pass it on to you, you can just see if you want to touch it. So these are the grains of zinc. Yeah, there was no mask there, so yeah, it's fine. I think it was not much. So these are the grains. Now you can see the grains on for the zinc. Zinc is the only material that you don't need microscope to see the grains. The transgranular is when it actually goes through the grain. It actually breaks the grain. It breaks the grain. The crack propagates through the grain. Okay, no worries. I'll go through that one. So you can see it's kind of looks like these things. Obviously, there is no failure. It's just to show you the grain structure. There is no failure. I just cut it with a saw. Okay. Now, in most brittle and crystalline material, crack propagates that result from a repeating breaking of the atomic bond. So transgranular failure, you will actually see the atomic bond being broken. Then we got the intergranular failure. Now, intergranular failures is typically due to elemental. If depletion, if there is chromium or something, it depletes on the grain boundaries, it weakens the grain boundaries, and then the grain boundaries is going to fail. Remember, the grain boundaries is the region of the highest impurity. No one wants the grain boundaries. So no one wants impurity. So this is one crystal structure, that one. This is one crystal. Now, this is one grain. Now it will push all the impurities towards the grain boundary. And this will push all the impurity towards the grain boundary. Now, what will actually happen is the grain boundaries will have all the impurities. When something has all the impurities, that will become weak region. And this is where it will fail. And you can actually see here, it's not very obvious, but let me draw that one. You can see here, these are grain boundaries failure. You can see that was a grain boundaries, and it just kind of failed at the grain boundaries. Now, if you have any metal, any material, it's polygrain. Many grain structures are there. Excuse me. And if you leave that one outside, where the corrosion will start, it will start at the grain boundaries. If you apply the stress and try to break it, the weakest points are the grain boundaries. So we need to make it strong. When we study the fracture mechanism, we study based on the material properties. We also study based on the stress level. We also study based on the crack production, like how the crack produces the flaws and how the crack propagates, intergranular, transgranular, or so on. Initially, when they make aeroplanes, obviously the aeroplanes have square windows. And then they were failing and they couldn't figure out the reason. So what happened is later on, they actually figure out, okay, because they are square, there's a crack concentration at the corners. Hence, they are not square anymore. So they kind of put a little bit curve on the side. So now to just decrease the stress concentration area. Okay. Now, when we have a look at the brittle material, we can do the theoretical calculations. Based on the theoretical calculation, we can find out that at what level, at what stress, at what load the material is going to break. But when we do in real life experiment, they fail at much lower stresses or at much lower forces. Now, the reason because they fail at much lower forces is because in theory, we didn't consider microvoids. We didn't consider when someone is making the object casting or whatever, there are air bubbles entrapped. There are some impurities. There are some flakes in there. There are some other material. So we don't consider that thing, and hence the results are a little bit different. Okay. Now, even if there are teeny cracks, or if there are any impurities, or if there are microvoids, air bubbles, tiny air bubbles, that act as a stress concentration area, which will amplify the stresses at that specific point. Hence, it will create a localized stresses, and that localized stresses will create a crack tip. That crack tip will propagate and hence fail the material. Now, there is a thing called fracture toughness. Fracture toughness measures the material resistance to brittle failure if the crack is present. It's also measures, it also defines the amount of the stress required to propagate if there is pre-existing flaw. Now, that flaw can be a microvoid, it can be a metallurgical inclusion like any other metal, it can be a defect because of the welding, it can be a defect because of the design, or it can be combination of all. Now, then we use a technique if flaws are present, we use a technique. It's called LEFM, linear elastic fracture mechanism, and that is used to design a critical component that can help us to avoid the failure. What we do in that technique, LEFM, we just make sure there are no stress concentration area. We make sure their curves are included. We make sure the material thickness is adjusted so it can withstand certain amount of loading and it doesn't fail. Okay, when we compare the ductile and the brittle, stress risers, the point which give rise to the stresses, it's more significant in brittle than in ductile. The ductile, the reason is if there is stress concentration, if that material, the roof is made of ductile material, and they're going to fail, I'll look, oh yeah, it's failing here. Okay, everyone out, we got time. But if that's brittle material and there is a crack, yeah, let's imagine that's made of glass, very brittle material, and there's a crack, and I'll be here. I saw the crack, the time I saw the crack, and until it propagates that one, that will be minimum maybe 1 second or something, and that whole structure will fall. So it doesn't give us any warning. So stress risers is more significant there. If you got ductile material, the plastic deformation, which is a permanent deformation, will occur when you exceed the yield strength. Yield strength is a material that when you start, the material start to yield. Yeah, material says, okay, I can't take it any longer. I will yield. I will start a plastic deformation. For example, imagine this is a ductile material. Imagine this is it's not ductile. Imagine it's a ductile material, and if I'm bending it, this is elastic, comes back, elastic, come back, elastic, come back. But imagine if I got another material. Now, if I just bend that one, now it doesn't come back. Yeah, because it's not coming back to its position. Yeah. So this is called the permanent deformation. Well, that's the book, but in case of other material, there are some material which are super elastic, super plastic. We talk about these one later. Okay. Okay, now if we have a look at the stress concentration factor in some of the material, it might be uniform in some materials, it might not be uniform in some material. Now, maximum stress concentration area will be, stress concentration factor will be less than the theoretical value of the one we've calculated for the brittle material. Okay. Brittle material, you won't see any yielding or any distribution, stress distribution. You do that one, it will snap, it will break. Now, if you have a look at this bit, this chart, you got the materials on this side, you got the yield strength in megapascal. We look at the megapascal rather than KSI. And then we got the KI. K stands for stress intensity factor. Stress intensity factor is used to find the fracture toughness of the material. Yeah. So we look at this bit. Yeah. These are the megapascal one or the one we're looking into. So they got different alloys and they got different stress yield strength. So if you have a look at the aluminium 7075, you got 495 megapascal. Mega is 10 to the 6. Now, if we have a look at the stress intensity factor, it's 24 megapascal. So if there is a crack, the crack will propagate. If the strength, if your force increases, stress increases more than 24 megapascal. Other than that, no, it's fine. But if there's a crack, it will make it super weak and so on. If you have a look at the steel, tempered steel at 425 degree, its yield strength is 1420 megapascal, but its stress intensity factor is 87.4. So it will fail at 87.4 if there's a crack. And then there are concrete and the other one. Obviously, concrete, soda lime glass, and aluminum oxide, they have no yield strength because they are brittle material. Yeah, but if there's a crack, they will fail. So have a look at the brittle material. The brittle material have a very low value of the stress intensity factor. Yeah. And if you compare that with polymers, you can get an idea. And if you compare that with metals on the top, just to give you an idea. Okay, next one. Now, stress intensity factor. It's used to determine the fracture toughness of the material. Okay, now we got the mode 1, the mode 2, and the mode 3. Now, the mode 1, now I'm applying the force on this direction. So you cannot see. So the force is being applied in this direction. You can see the arrows. Okay. Now the crack is normal to the direction of the largest tensile strength. Now, if you have a look at the mode 2, it's different. It's more like a shear force. And if you have a look at that one, it's more like a torsional force. Now, the formula is this. The stress intensity factor is represented by this one, Ki equals sigma square root of pi alpha b, or pi ab, where K is the fracture toughness, sigma is the applied strength in megapascal, A is the length of the crack, yeah, in meters, because if we're using megapascal, we use meters. B is the crack length, and the component geometry factor. That's different for different component. Yeah. So B is a crack length. Yeah. And component geometry factors. They are two different things. Okay. Now then there's a critical stress. Now when we have a look at critical material, now the critical material, all brittle materials contain a population of small cracks. They are present with different size, different geometrical orientation. Stress intensity factor, which is a K, depends on the geometry, depends on the load. Yeah, I can change the geometry shape and I can apply the same load, same material, it will fail at less stress. Yeah, Kc is fracture toughness. It depends on various factors, material, it depends on temperature, it depends on environment, it depends on rate of loading. Rate of loading is like that, yeah? So you apply a sudden loading or uniform loading. Okay. Now, if we have a look at that one, not this one, this one. This is a compact tension specimen here. So what we do is we create a notch and we apply a force and we just break the specimen. It's not very obvious here, but I show you the equation actually. Okay. This is the equation of the crack propagation. Now, we assume the crack is elliptical shape. Now, if we want to find out the maximum stress, the formula is 2 sigma naught A over rho T square root equals KT sigma naught, where rho T is the radius of the curvature, is that radius. Oh, sorry, can you see my cursor? No, you can't. Okay, let me just change that to laser pointer, that one. So it's this part, this is a rho T. Stress applied is that one, sigma naught, that's a stress applied. And A is the length of the crack. Yeah, so the total is 2a, so a is half of the length of the surface crack. Yeah, okay. Sigma m over sigma naught is called the stress concentration factor, KT. The crack, when the crack will grow. When you design the material for failure or for prevention of failure, if K is greater than or equal to Kc, the crack will grow. Yeah, and K is that's another relationship. Okay. Now, when we consider the design factor, stress design, if we want to, if there are multiple cracks, the largest crack will break. The material will break where the crack is largest in size. Now, let's have a look at the first one, where we have a look at the maximum flaw size, the flaw size, how we can say like, okay, this material should have a flaw size of that. That's the maximum allowable flaw size. If it's more than that, no matter what, it will fail. Okay, this is the design stress. Design stress should be less than Kc over y divided square root of pi a max, maximum allowable, that one. So if there's a crack size and we know the value of the crack size and we know the Kc, we can put that one. It will give you the design stress, that is the stress the material is going to fail. Or if you got, let's say you say, okay, I want this piece of rod, it should hold a maximum stress of 90 megapascal. So this is, I'm designing for 90 megapascal, and I have the Kc value, yeah, which is the ratio, and I have all this value, and that will give you, okay, the maximum crack size should be not more than 5 millimeter or something like that when we put, and then we can have that one. So what does it mean? If you have an aeroplane or something, yeah, and you know that it can fly up, and when it flies up, it's under high stress, and if there's a tiny crack in which is 1 millimeter, and according to your calculation 5 millimeter crack is fine, what you do is the people, they put aluminium tape on that one. That's how they repair it. Yeah, they don't bother with that crack. But if the crack is 4 centimeters, something like that, then they will say, sorry, no, don't take off, because at that 4 5 millimeter crack is going to cause this plane to crash. Okay, so you can actually have a look. If it's below, that's a graph which says like it's the ratio between stress, the y-axis stress, and this is the maximum crack size. If it's above this line, the fracture will occur. If it's below this line, the fracture will not occur. Yeah, same for that one. Yeah. Okay, now the material, this is what I was talking about with aircraft wing. Now the material has Kc of 26 megapascal. To design A is largest flaw is 9 millimeter. The failure stress is 112 megapascal. Yeah, so we're going to use that one, and we can actually calculate. We can calculate all the bits. We can just put the values. We have the value for this bit. Yeah, A maximum 9. Yeah, we have the Kc value, which is that one, and we can figure out like what is the maximum stress concentration. Yep. So it will be 168 megapascal. Yeah, that's the critical stress. Yeah, so we can just work this one out. Yeah, so put that one, find this one up. Yep, so this is one. That second is this one, same material, flaw is 4 millimeter. Failure stress we need to find out. Yeah, for 9 millimeter it fails at 112. For 4 millimeter, where it will fail, you can see the crack size is reduced, but the stress is increased. So now it won't fail at 112. It will fail at 168 or 170 and so on. Okay, if you reduce the flaw size, it will help you to use the same material under high loading conditions. Yeah, so reducing the flaw size pays off. Yeah, okay. Now then there are sensors. Now there are sensors, piezoelectric based sensors. We use strain gauges, which is inbuilt into the aeroplanes. And we use that one for structural health monitoring, or SHM, we call it. Now, these sensors, if they are abnormal crack, if there are abnormal strain, it can measure, it can feed back into the system. You might have seen in the city center, the buildings, big buildings, old buildings, they actually attach a piece of wire on that and that end, and they actually attach it. And in the middle, they actually put a kind of like a tiny meter. It's just the same size of, the meter is same size as of what you call, that size. And as it because if that building is falling or the crack is getting bigger, the load will be bigger, and it will be mentioned here. Yeah, so it records the reading. Tamar Bridge, they got really good fiber optic system. Any change in length is recorded. Any crack propagation is recorded. It's one of the state-of-art bridge in the whole UK, the Tamar Bridge. Okay, now if I show you next one, so this is aeroplane. All these parts where you can see, these are all the strain gauges, which is something like this. They are attached. Okay, we can have even a self-adhesive CVM kind of, it's called comparative vacuum monitoring system. We can attach that one. We have a similar system in banks and everything. So they put that one in the windows, inside the windows. So if there's a crack in the window, yeah, that's what they're not worried about, the crack. They're worried about if someone will break the window and come inside. It will trigger the alarm because the stress is so much. Even if someone is trying to push that one, high wind condition, it will trigger the alarm and so on. Okay, I will skip this bit. How do we actually find out the cracks if they are not visual? We do some non-destructive evaluation, NDT method, but I will skip that one for some of the time. Okay. If we have a look at the brittle fractures of ceramics. Now in ceramics like cup, porcelain, they will break if you apply if let's say you have a diamond indenter and you're applying the force, let's say, at that end, the crack will start and it will propagate at this region, and it will cause failure. This is impact failure. It will look like this. If the failure is because of bending, the crack in the ceramic will look like this. If it's in torsion, the crack will look similar to it's in bending. If it's because of internal failure, that's how the crack will look like. So you can see the curves. Yeah. This is when the first thing, when you arrive at the failure scene or you do failure investigation, how things break. The first thing we do is we look at the visual inspection. We look at how the material has failed. We look at the shape and size of the crack, broken specimen. And based on that one, we can actually find out, was that the crack force was applied outside, bending force, was internal pressure, or was it torsion, and so on. Okay. Now, this is 300 micrometers. So 300 micrometer. Yeah, that's the microscopic image. Now, you can actually see this one. This is a silica rod. So imagine this is like glass kind of material, a very brittle fracture. You can actually see the crack originated point. You can see the mist region. This region is called mist region, and you can see the hackle region. Now, what actually happened is this is the point where the cracks start, where you can see this black kind of region. After this region, there is a thing called mist region. So you can see here on this graphical representation, where the cracks start to propagate. That's a massive force being applied here. when it starts to propagate, and then here the energy is distributed, and it created the Hackle region. So you can see the Hackle region here. This tells you the crack initiation point and how it actually propagates. Now, if the critical velocity is not reached, critical velocity is the velocity at which the crack is going to propagate. The crack is not going to propagate. Yeah, it has to reach that critical velocity. Okay. Same thing, the fractures in polymers. The fractures of the polymers are usually at quite low stress values. If you have a look at the thermosetting polymers, they are quite a cross-linking. Cross-linking means thermosetting polymers are much more stronger than thermoplastics. So thermoplastic polymers are, you can bend them. Thermosetting, they are HDP is kind of thing. Now, if we, thermoplastic polymers, they are both ductile and brittle mode possible, depends on the temperature. If you got thermoplastic, low temperature, freezing temperature, it will be a brittle failure. If you increase the strain rate, you sudden failure. So you can have a very plastic material, but if you apply a sudden force, it will break in a brittle fashion. But if you do very low, it will be in a ductile failure. If there are sharp notches present, it will be brittle. Okay. If you increase the thickness, it will be brittle. Now, there is a thing called crazing. Crazing is a phenomena of a plastic deformation, and it forms the microvoids and fibrillar bridges like that, yeah? And this phenomena is known as crazing. Okay, I think we stop here. Next time we will have a look at the impact testing. So we start from this slide 30, and we just work towards the next one.